the ideal gas laws. Today's lesson. Molar mass of gases. Gay-Lussac measured the volumes of gases before and after a reaction. He devised the law of combining volumes. When gases react, the volumes of the reactants and the products measured at equal temperatures and pressures are always in whole number ratios. So what we're going to see is when we look at the number of moles, and we're putting together, right? We're putting together hydrogen gas and oxygen gas to form water, right? So if you look at the ratio of atoms that we use to form our products, he found out that their volumes equal those same amounts. Okay, so 2 volumes of hydrogen gas react with 1 volume of oxygen gas to produce 2 volumes of water vapor. And these numbers coincide with the number of moles found when we're putting together 2 molecules of hydrogen gas, 1 molecule of oxygen to form 2 molecules of water. So these numbers, these coefficients, right, that represent the number of moles or the number of molecules in this equation also correspond with the volumes of their gases. Okay, so you can kind of see how this is ultimately going to lead into gas stoichiometry. So John Dalton examined the masses of compounds before and after reactions also. Dalton's research led him to propose the law of multiple proportions. The masses of the elements that combine can be expressed in small whole numbers. Small whole number ratios. So very similar to what we were talking about, the number of moles for each reactant to give us the number of moles of a product. But these moles also coincided to their volumes. Okay. So Avogadro combined both Dalton and Gay-Lussac's ideas and related the volume of a gas to the amount that is present. And so he's looking at the idea of calculating their masses. And using that, we were able to pretty much calculate their moles. And ultimately, using the number of moles and being able to find the molar volume, okay, of these reactants and these products. Avogadro divided Dalton's mass ratios by the molar mass of the elements to obtain the mole ratio. So remember, if we get the mass and divided it by the molar mass, right, that whole molar mass is equal to mass over number of moles, right? So he was able to use the same principle for these gases. Now, what he noticed that was that 1 liter of hydrogen gas reacts with 1 liter of chlorine gas. So we're looking at the assumption that, well, if we looked at it in terms of 1 mole, we were also able to figure out that also it corresponded to 1 liter reacting with 1 liter of chlorine gas. And I'll show you guys as we move on a few of these ratios. Avogadro decided that there must be the same number of molecules in each liter of gas. So Avogadro's hypothesis was formulated as follows. Equal volumes of all ideal gases at the same temperature and pressure contain the same number of molecules. So if we had, like that example, 2 moles of hydrogen combined with 1 mole of oxygen, we can still relate that to 2 liters of hydrogen gas combining with 1 liter of oxygen gas to produce 2 liters of water. Okay, so he used pretty much those same ratios for the for volume as well, not just for moles or number of molecules, but also for their volumes if they were at the same temperature and pressure. Remember, that had to be consistent. So notice that the mole ratios are the same as the volume ratio. So here we have the example that we talked about. So if we look at the balanced equation of hydrogen gas combined with oxygen gas to produce water vapor, right? We had a ratio of 2 to 1 in terms of hydrogen to oxygen gas to form 2 molecules or 2 moles of water vapor. So notice we had 2 moles to 1 mole to 2 moles. but we can also relate it to two volumes, so we can look at it at any type of volume, right? 2 liters plus 1 liter of oxygen will produce 2 liters of water vapor. Okay, so notice how these mole ratios corresponded to the same, but we're looking at now in terms of volume. Okay, so today our knowledge of atoms and molecules helps us understand Gay-Lussac's results. We know that gases are made of molecules that may contain more than one atom. Right? So we have here 2 atoms of hydrogen, 2 atoms of oxygen each to form the one diatomic molecule, but when they combine together, they form a completely different molecule. But again, the ratios that we use, the mole ratios, correspond to their volume ratios. Okay, so here's that example that we talked about, the hydrogen gas and chlorine gas to form hydrogen chloride gas. Right? So what we have here is, it's a 1-to-1 to form 2 molecules, or 2 moles of hydrogen gas. But now that also translates to let's say 1 liter, hypothetical 1 liter, 1 milliliter, whatever the volume of the gas is. But if we had let's say 1 liter of hydrogen gas, will combine with 1 liter of chlorine gas, but in the end, we're going to form 2 liters of the combined gas when we put them together. Right? So when we see this ratio in a balanced equation, we can treat it as 1 mole and 1 mole, or 1 liter and 1 liter to form 2 liters. Right? So we can pretty much use the same ratios, but now instead of mole ratio, a volume ratio. Same thing here goes at the bottom here. We've got hydrogen gas combined with nitrogen gas to form ammonia gas. So if we look at the balanced equation, right, we've got 3 moles of hydrogen gas combined with 1 mole of nitrogen gas to form 2 moles of ammonia gas. Right? So we can treat it the same way, where instead of treating it as 3 moles, we can look at it as a volume ratio and go, well, we have 3 liters of hydrogen gas will combine with 1 liter of nitrogen gas to form 2 liters of ammonia gas. Okay, so notice the ratios we use can interchange with volume or moles. So, Avogadro's law. Avogadro's law gives us a mathematical relationship between the volume of a gas, V, and the number of moles of gas present, which is N. So, N is going to represent the number of moles, V is going to represent our volume, K is going to represent some kind of a constant. So, N, the number of moles, is proportional to V. So directly proportional, which means we have N, the number of moles, is equal to some constant multiplied by the volume, right? Which means if we increase the number of moles, we'll also increase the number of, or pretty much we'll increase the actual volume as well, right? So it's a direct proportion. So we can relate it to the following equation, right? So the number of moles, 1 over the initial, so we could treat this, instead of 1 and 1, we could treat this as I, right? Our initial number of moles divided by our initial volume equals to our final number of moles and our final volume. So treat the equation similar to when we looked at the gas laws, but this is now the Avogadro law. Okay, so we looked at Boyle's law, Charles' law, Gay-Lussac's law. Now we're looking at the Avogadro law. And the Avogadro law looks at the number of moles and the volume. Based on Avogadro's law, 1 mole of a gas occupies the same volume as 1 mole of another gas at the same temperature and pressure. So the STP here, as we talked about in previous, right? So if we're looking at a standard temperature and pressure, right? Or we're just looking at it as just at any random temperature and pressure, but they have to be consistent for the initial and final results. So the molar volume of a gas is the space that is occupied by 1 mole of that gas. Right? So if we're looking at something, right? We're looking at a certain volume, but we're not given. We'll assume it to 1 mole of that substance, and you'll see that when we go into some of the practice problems later on. So molar volume measured in the following units. It's liters per mole. Right? So don't mistake it for molarity, which is moles per liter. Right? So molar volume, right? We're focusing on the volume, liters per mole as opposed to moles per liter that we've seen before, but that's molarity, right? Concentration. Now, we can find the molar volume of a gas by dividing its volume by the number of moles that are actually present. So notice here, V over N, very similar to the Avogadro law, right, where we had N over V, right? But it depends on what we're trying to find. But if we're trying to find molar volume, it's volume over N, but don't mistake it with the Avogadro law, which is N over V. And that's really if we're trying to find an initial state and a final state. Okay, so let's look at the first sample problem. A resealable 1.30 liter container has a mass of 4.73 grams. Nitrogen gas, which is N2, is added to the container until the pressure is 98.0 kilopascals at 22.0 degrees Celsius. Together, the container and the gas have a mass of 6.18 grams. Right? So the container and the gas itself together. So that's the container is 1.3 liters. Okay. We've got the mass of the container with the nitrogen. So calculate the molar volume of nitrogen gas at STP, standard temperature and pressure. So take a moment and try to list out what you have, but look at the initial state and the final state. Okay. And try to figure out the molar volume of the nitrogen gas. Let's point out some of the information. So we've got our initial pressure, which was 98.0 kilopascals. We've got the initial volume, the container, 1.30 liters. Initial temperature, 22 degrees Celsius, which translates to 295 Kelvin. We have a mass. Now, what is the actual mass of the nitrogen? Because if we look at 4.73 grams represents what? The mass of what? The actual container. The 6.18 grams represents both the container with the gas, right? So we want to subtract these two. Right? And what do we get? We get 1.45 grams. So grams of the nitrogen. Right? So which means we are really trying to find the number of moles, because we're trying to find the molar volume. So it's volume divided by the number of moles, right? So we need to find that, right? So now, final pressure. We've got, actually let me use a different color here. So we've got our final pressure at STP is, and remember, 101.3 kilopascals. So hopefully all that work wasn't for nothing if you didn't know that. The volume, that's what we need to find, right? Because for molar volume, volume divided by the number of moles. We have our final temperature. What is the temperature at STP? 0 degrees Celsius. Go back, folks, and make sure you remember these numbers. Okay. which is equivalent to how many Kelvin? 273 Kelvin. The mass, right, still the same, 1.45 grams, right? And we're trying to find the final. So in fact, the number of moles of the initial will be equal to the number of our moles in the final. It's not really going to change, right? Because the only thing that's going to change is the final volume. So the volume can change, but the number of moles that we had it, right? Imagine you're putting, 5 moles of a gas in a container, in a big container, a 10-liter container. And then you're changing the gas, and you're putting it into a container that's even smaller, right? All we're doing is putting all the particles even closer together in a smaller container. But the number of moles hasn't changed. The volume has changed of the gas. Okay? Because remember, the number of moles, that doesn't change. So if we look at our calculations, right? So what we have is the following. We've got the initial pressure. Right? So we're looking at combining the gas laws from previous class, right? So our initial pressure, volume, temperature equals to our initial, is equal to our final pressure, volume, temperature. But we're trying to find the final volume. So what we want to do is we want to isolate for VF. So we're going to isolate for VF, right? So VF is equal to PI, VI over TI. But now we're going to move temperature from the denominator here to the numerator. So we're going to add that there. We're going to bring this pressure down to the numerator when we move it across the equal sign, so it will be moved in there. So now all we got to do is substitute initial pressures, volume, temperatures into this equation. So we have VF is equal to our initial pressure, 98.0 kilopascals. Like I said, try to use the units. It's easy to follow along. Multiplied by our initial volume, 1.30 liters, multiplied by our final temperature, which is 273 Kelvin, all divided by our initial temperature, which is 295 Kelvin, multiplied by our final pressure, which was 101.3 kilopascals. Okay, so let's look at the units that cancel. Kilopascals, Kelvin, and all we're left is with liters. So when we multiply all that together, right, we get the following. We get the following. Final volume is going to equal to 1.1639 liters. So that's what we're going to get for when we multiply all that before it got erased from the screen. So now we've got the volume, right? We needed to find the number of moles, right? To do that, what information do we have of nitrogen? Well, we have the volume, but of nitrogen specifically. We knew the mass was 1.45 grams, right? So now I want to find the number of moles. So how can I do that? What do I have to find? The molar mass, right? And the molar mass of nitrogen is 28.02 grams per mole. So what function am I going to do between mass and molar mass? Divide them, right? I'm going to divide those two. So N is equal to 1.45 grams divided by 28.02 grams per mole. Right? Grams cancel out, and the number of moles that I get is 0.0514 0.75 moles. So now I have my N value, the number of moles. I have my volume. I'm being asked for the molar volume. Right. Molar volume is volume over the number of moles. So we've got 1.1639 liters divided by 0.05175 moles. So the molar volume, when we throw that into the calculator, we get 22.49 liters per mole. Okay, so based on number of significant digits, we've got 3 significant digits. 22.4 is what we want. We look at the 9, so it becomes 22.5 liters per mole. Okay, so that's the molar volume of nitrogen gas at STP. Theoretically, what we didn't get the exact number that we're really looking for, and I'm going to show you guys in just a second. But we got something pretty close. Okay, because all gases, as we're going to see, right, the actual molar volume is as follows. Molar volume of an ideal gas at STP is 22.4 liters per mole. What did we get with our example? 0.5 liters per mole. And it all depends on, when we round it off and all that. That all plays a big role in our final answer. But really the number you should remember is the following. When you're being asked for the molar volume at STP, standard temperature and pressure, that is the molar volume we're going to use. 22.4 liters per mole. We're going to see a few others. Okay, so let's try this next sample problem. What is the volume of 3.0 moles of nitrous oxide, NO2 gas, at STP? So, what we want to do is pretty much let's list the information. So we've got volume, 3.0 moles, okay, of nitrous oxide. All right, so we've got an N value, which is 3.0 moles. Now, we want to find out what the initial the initial number of moles is, right? So, at STP, what was the molarity? So if we're looking at it, we're going to treat it as if it's 1 liter, or 1 mole. Because what is the volume at STP? What did we just calculate? 22.4 liters per 1 mole, right? So what is the volume at STP? 22.4 moles, right? Because if we divide this by, what did I say moles? Liters. Because if we divide that, 22.4 liters divided by 1 mole, we're going to get the molar volume at STP. So we're trying to find now the actual volume of 3.0 moles. Right? So in reality, how many times are we increasing it by? We're increasing the number of moles 3 times, which means how many times am I going to increase my volume by? By 3 times as well. But what we're going to do is, what law kind of shows number of moles, initial, final, number of the volume, initial and final? Learned that today, and that's the Avogadro. So we are trying to isolate for VF. Right? So VF is equal to NF times VI over NI. And all it is just pretty much rearrange it. Remember what we said, what we can do? We can switch these two, right? So we can put our unknown at the, in the numerator, because that's where we want to do to isolate it. So our final number of moles, 3.0 moles, multiplied by our initial volume, which is 22.4 liters, divided by 1.00 moles. So notice here, moles are cancel out, and our answer is going to come out to 67.2 liters. Least number of significant digits in my question is 2. So we want the 67, we look at the 2, so the answer is 67 liters. So notice how 1 mole is equivalent to 22.4 liters. 3 moles is equivalent to 67 liters. So imagine if we multiplied this by 3, this by 3, and we would get a number. So so pretty much the numbers coincide. Remember what we said, right? The ratio or the proportionality between the number of moles and the volume. If the number of moles increased, so did the volume. So the number of moles increased from 1 to 3, which means it was a 3-time, proportionality, right? So which meant that the volume also was going to increase by 3 as well, and it did. We proved it with our calculation. So make sure that also when you do the calculations that you actually look at it and go, okay, do the numbers make sense based on these proportionalities? Okay, so if my number of moles has increased, am I seeing the same ratio of increase with my volume, and vice versa? So, suppose that you have 44.8 liters of methane gas at STP. How many moles are present? What is the mass in grams of the gas? And how many molecules of gas are present? So, I'm going to actually go through this one with you guys. So, I'm going to take this step by step. So we want how many moles are present. So what we have pretty much is we've got 44.8 liters of methane gas, but now it's at STP. So at STP meaning 22.4 liters, 1 mole. Right? So we've got our initial number of moles, right? 1.0 moles. Our initial volume is 22.4 liters. Our final moles, right, is what we are asked to find, and our final volume is 44.8 liters. So we have the equation Ni over Vi equals Nf over Vf. Okay, so we substitute what we're trying to do, isolate for Nf. So the final number of moles is equal to Ni multiplied by our final volume over our initial volume. So what do we get? 1.00 moles multiplied by our final volume, which was 44.8 liters, over our initial volume, which was 22.4 liters. So notice liters cancel out. When we multiply these, we get 2.00 moles. Now, does that make sense, though? Does that make sense, right? Because we went from an STP volume of 22.4 to a final volume of 44.8 liters, right? So we went by, it went up 2 times, right? So which meant that the number of moles that we started with, 1 mole, right, increased to 2 moles. Okay. So we'll keep that that answer, 2.00 moles, to help us out for the later question. So let's put that in here, 2.00 moles. Okay, So now, what is the mass of the gas? Well, to do that, what is methane? What is the formula for methane? CH4. So we want, what do you think we're going to need to find? Molar mass, right? Molar mass, to pretty much save you guys the time, is 16.05 grams per mole. Right? We want to find the actual number of grams that are actually present. Right? So we've got the molar mass, we've got the number of moles that we found in part A. So what can I do? So mass is equal to molar mass times the number of moles, right? So the molar mass, 16.05 grams per mole, multiplied by 2.00 moles, right? Notice moles cancel out, and I'm left with 32.1 grams. Right? So we still keep it to the 3 significant digits, even though that question had no more, no additional numbers to change. So we're keeping the 3 significant digits going. Now, part C asks us for how many molecules of gas are present. Right? So now, from this, what are we looking at? What number should come to mind? Exactly. The number of moles, right? The actual, so it's 6.02 times 10, right? 6.02 times 10 to the power of 23, right? And that translates to, this tells us how many molecules there are, right? Molecules per mole. So if we take that and we're going to multiply it by what? To find the number of molecules. The number of moles. Right? Because it's molecules per mole, but it's molecules per mole. Right? If we multiply them, look, moles cancel out, and it'll give us the number of molecules, which is equal to 1.20 times 10 to the power of 24 molecules. Okay. So that is the number of molecules of gas present. So, volumes of real gases. Ideal gases have a volume of 22.4 liters at STP, right? Something what we calculated before, it was close enough. But notice here, that whole close enough, right? Here is the molar volume of various gases at STP. And notice how they're not exactly 22.4, but they're pretty much ballpark, just like what we calculated with one of the previous examples. You don't need to memorize. The only thing you do need to memorize is the ideal molar volume of an ideal gas is 22.4 liters per mole. Right? So, did I write it down here? Yeah, so 22.4 liters per mole, which is equal to, right? So 22.4 liters per mole can be broken down as a volume, that is 22.4 liters, and the number of moles of 1.00 moles. And the reason why I put 1.00 moles instead of 1 mole is because, well, I've got 3 significant digits here. I want to keep it consistent. Right? Because if I was to do this calculation, 22.4, and I didn't put that, then technically I would be rounding it to my to 1 significant digit, my answer. And we don't want that. We want to keep the 3 significant digits. Right? So that's why we include the 0.00. Okay. So here we have various gases, helium, nitrogen, oxygen. Right? Notice how they're all 1 mole. Their pressures are all the same. Their temperature all at 0 degrees. Notice What is different with all of these? What is different? Their mass is always different, right? Because their molar mass will also be different, right? Because it's all based on, well, we've got helium, we've got nitrogen, we've got oxygen. So their mass is going to be different, but notice what is always the same at STP. Temperature, same. Pressure, the same. Number of moles, the same. So the only thing that's going to be different is their mass. And ultimately, what we're going to look at in the next chapter is the density. And notice how also the density is different with all these gases. Okay, but their molar volume exactly the same at STP. So, real gas deviations. At STP, most real gases behave like ideal gases. Right? I'll explain what the differences are. However, at high pressures and or low temperatures, gases no longer behave ideally. Right? Because realistically, right, if I lower the temperature of a gas, what really is supposed to happen? Particles of the gas are always moving really quickly, right? As I lower the temperature, what happens to that kinetic motion? Slows down. And realistically, what does happen to that gas? Think elementary, right? Turns to a liquid, right? Realistically, real gases do that. Ideal gases just move slower. But we're going to treat it that. So that's really the difference. When you see real gas and ideal gas, think ideal gas is the idea that the gas still stays as the particles that they remain as. That they do not condense into a liquid. A real gas will condense back into a liquid. Okay. So, recall the characteristics of an ideal gas according to the kinetic molecular theory. Gas molecules have insignificant volume of their own. Molecules have no attractive forces between each other or with their container. Right? So they're not going to kind of want to come together. Molecules move in perfectly straight lines, and collisions are completely elastic and thus do not use up any energy. So that is pretty much the derivation of the ideal gas, the idea of an ideal gas. Now, these characteristics led to the ideal gas law. Now, the only thing is, the following actually happens. Particles of a real gas have a significant volume of their own. Molecules actually do attract to one another. There is a force of attraction between gases, even though we think that they don't. Molecules do not necessarily move in a straight line. Collisions are not completely elastic. Okay? So in fact, right, two molecules do actually have this attraction. This is called the van der Waals force, which I don't know if we may talk about it if we've got time, but you will kind of go into it a little bit more detail in the grade 12 course. At high temperatures and or low temperatures, gases have small volumes. Since the gas molecules are closer together, the molecules interact more than they are when they're farther apart, right? Because when you're pushing them together, right, they have to somehow work with one another. Right? So there is an attraction the closer you get these molecules. So when you get these molecules closer together, you do that when you lower the volume, right? So you've got a big container, you shrink it. You're forcing the gases to kind of work together, right? And you'll see that kind of an attraction occurring when you change the volume and, of course, when you lower the temperature. It is no longer true to say that the molecules have no attractive forces between each other and with their container, because in fact they will. They will actually have this attraction, these van der Waals forces. Now, since the total volume is smaller, the amount of space taken up by the gas molecules is more important. We can no longer ignore the volume of a gas molecule. Okay, so in summary, at low pressures and high temperatures, most gases behave as ideal gases. Okay, so at high temperature, right? High temperature, meaning really fast particles, ideal. Right? It's in the gas form. It's not going to condense. It's going to continue to move even faster and faster. It's going to increase its kinetic motion. Under any condition that allows attractive forces between molecules to occur, gases no longer behave as ideal gases. So what's happening here now is we are going back to that realistic idea of a gas, that if we lower the temperature, the particles really, they're not going to stay as a gas. They are actually going to condense and come together to form that liquid, which there is an attraction with that liquid, right? Those particles, there's an attraction, right? That's what keeps the water molecules together, right? And then ultimately to a freezing point. Okay. And instead, they behave as real gases. So as we said, if we lower the temperature, right? Think about the Kelvin scale, right? The idea that if the temperature continues to lower, right, all of a sudden the kinetic motion is supposed to cease, right? So it cease to exist. But we know that if the particles lower in temperature, gases will ultimately condense. We continue to lower that temperature of that liquid now, it will freeze to that solid. Right? That's realistically. So real gases do that. Ideal gases just slow down their movement. So arriving at the ideal gas law, we know that volume is proportional to the number of moles. We know that volume is proportional to the temperature over pressure, as we looked at in the previous, right, in the combined gas laws, right? So we've got Avogadro, combined gas law, right? Now, we know that using that, so volume is equal to, right, the number of moles times the temperature divided by the pressure. So we're combining, right? So treat this as if V is equal to N, but V is also equal to T over P, we're throwing N into the mix of this proportionality to give us this part of the equation. Right? And ultimately, we're going to have the constant. Remember how we had the constant of K? But the constant here, we're going to treat it as the constant R. And R is a universal gas constant, and it's a specific numbers that you're going to have to memorize. Okay. And it combines the pressure, volume, number of moles, and temperature. So let's look at the ideal gas law equation. Is PV is equal to nRT. Okay. So pressure, volume, number of moles, temperature, and a constant that you're going to have to memorize. Okay, I'm going to show you guys actually how to get to that R value without having to memorize it, but little change to the answer, to the numbers that we're using. I'll show it to you when we actually get to it. So, for 1 mole of gas at STP, pressure, what is the pressure at STP? 101.3 kilopascals. What is the volume at STP? 22.4 liters. What is the temperature? 0 degrees Celsius, which is equivalent to 273 Kelvin. And the number of moles? 1. Right? 1.00 moles. So now, using the equation, PV is equal to nRT, what do you think we're trying to find? What that R value is. So what we're going to do is we're going to isolate for R. R is equal to PV over NT. Right? So we've got pressure, which is 101.3 kilopascals, multiplied by the volume, which is 22.4 liters, over 1.00 moles, times 273 Kelvin. Now, do any of the units cancel out? No. Right? What are the least number of significant digits here? 3. So when you throw that into the into your calculator, you're going to get the following: 8.31 kilopascals times liters over moles per Kelvin. So this is your R value. This is the constant you need to remember. 8.31 kilopascals. Okay. But in fact, I'm going to add an extra significant digit. Just hold on. I'm going to add an extra significant digit. So we're going to treat it as 8.314 kilopascals per liter per moles per Kelvin. Okay. Guidelines for using the ideal gas law. Always convert the temperature to Kelvin, right? As we've talked about with Charles' law and Gay-Lussac's law. Always convert the masses to moles. Always convert the volume to liters. Right? So if you have milliliters, change it to liters. And when using the ideal gas law, okay, it will be easier if you always convert the pressures to kilopascals, as we have in the value of R. So notice the value of R is 8.314 kilopascals per liter, or times liters, over moles of Kelvin. Right? So make sure, notice as we said, pressure in kilopascals, volume in liters, moles, and our temperature in Kelvin. Okay, so make sure that you do use these units. Okay, converting the units of the universal gas constant. So what happens now if you have to make the changes of R? And as we said, we want to try to keep pressure as kilopascals, volume as liters, moles, and temperature as Kelvin. But what happens when we have to change the actual pressure? So what we're going to do is what happens if the pressure is actually given in atmospheres? So we know that 1 atmosphere is equal to 101.3 kilopascals. So when we write it down, we want to write it down. So we've got kilopascals, right, is the unit that we want to cancel out. So when we multiply it, kilopascals is in our numerator. So to cancel that out, we want to put the kilopascals in our denominator, which means we're going to have here up at the top 1 atmosphere. So 1 atmosphere is equal to 101.3 kilopascals. Kilopascals cancel out, and we're going to get an R value of 0.08206. But now notice the units is going to be atmospheres of liters per moles of Kelvin. So this is if you're giving your pressure in atmospheres. But now what happens if you're giving your pressure in torrs? So again, same thing, we're multiplying, right? Kilopascals are the units of pressure we want to remove. But we know that 101.3 kilopascals is equivalent to 760 millimeters of mercury, right? Our torr unit. So what we're going to do is we want to cancel out kilopascals, so we're going to put the 101.3 kilopascals here at the bottom to cancel it out, and it's equivalent to 760 millimeters of mercury. So our units for R is going to equal to 62.37. And now notice the units here will be millimeters of mercury, okay, of liters per mole of Kelvin. Okay, so your best bet is to change your R value accordingly, especially if you're being asked to maybe convert your units. If you're asked to try to find the pressure or try to find something, and you want to keep the units going, and it might be easier to just change your R value. So let's look at the following sample problem. Use the ideal gas law to calculate the molar volume of a gas at standard ambient temperature and pressure, SATP. The conditions for SATP are 298 Kelvin and 100.0 kilopascals. So take a moment and think about how to go about solving the following problem. Okay, so what we're trying to do is find the molar volume. So what's important is that we have pretty much what is our given. So we've got pressure is equal to 100.0 kilopascals. We've got a volume, which is what we need to find. We've got the number of moles, and the number of moles we're looking at will be, because we're looking at a molar volume, so it'll be volume per mole. That per mole means 1 mole. All right, we've got an R value, which is 8.314. That's the constant we have to memorize. Kilopascals of liters per mole of Kelvin. And our temperature, which is 298 Kelvin. There's nothing we need to convert. So what we were trying to do here is rearrange the equation. PV equals to nRT. What we're trying to do is isolate for V. To isolate for V, move P across the equal sign. So it's V is equal to nRT over P. So let's substitute the numbers accordingly. So instead of N, have 1.00 moles multiplied by R, which is 8.314 kilopascals of liters over moles of Kelvin, multiplied by 298 Kelvin, divided by 100.0 kilopascals. So now let's look at what units get canceled out. So we've got kilopascals, we've got moles, we've got Kelvin, and the last unit standing is liters. So we throw all that into our calculator, and our volume is equal to 24.776 liters. Least number of significant digits in my question are 3, so I'm going to take the 24.7. So the volume is going to turn into 24.8 liters of our ideal gas. Last sample problem. Dentists sometimes use laughing gas, dinitrogen oxide, N2O, to keep patients relaxed during dental procedures. A cylinder of laughing gas has a diameter of 23.0 centimeters and a height of 140.0 centimeters. The pressure is 108.0 kilopascals and the temperature is 294 Kelvin. How many grams of laughing gas are in the cylinder? So take a moment and try to identify all the different units to help us find the actual mass of our laughing gas. So let's identify the information that we're given. Pressure, 108.0 kilopascals. Temperature, 294 Kelvin. Our volume is something that we're going to need to find. It's not given directly, but we can find it because we've been told that it's a cylinder of laughing gas, and so we're going to have to go back to our math skills and knowing measurement and trying to find the volume of a cylinder. We know that our R is 8.314 kilopascals of liters per mole of Kelvin, and so we're trying to find our N value when we're given PV is equal to nRT. So first things first, let's try to find the volume. And the volume of a cylinder is pi r squared h. So we're going to have our pi value. We're going to multiply it by our radius, but we are given the diameter, which is 23.0 centimeters. So we want to find half of that diameter to get our radius, which is 11.5. I'm going to square that. We're going to multiply it by our height, which is 140.0, and it's centimeters, and these are also centimeters squared. So when we multiply all those together, we get the following volume: 58,167. I rounded it off. Cubic centimeters. But remember what we said? Volume we wanted in liters. right? So 1 liter, right, 1 liter equivalent to 1,000 centimeters cubed. Right? So this will equal to 58.167 liters is our volume. So now what we're trying to do, we want to isolate for N, because using that value, we're going to try to find the number of moles, right? Because N is in moles. And using the laughing gas N2O, right, we can actually go one step further and find the molar mass of the N2O, which is equal to 44.02 grams per mole. So once we have the number of moles, we'll be able to use that part to find the actual mass of the laughing gas. So let's isolate for N. N is equal to PV over RT. So I'm trying to use a different color here. So our pressure, 108.0 kilopascals, multiplied by the volume, which we found, 58.167 liters, over the R value, which is 8.314 kilopascals of liters per moles of Kelvin, multiplied by our temperature, which is 294 Kelvin. So let's isolate the units here. Liters cancel out with liters, kilopascals with kilopascals, Kelvin with Kelvin. Last unit standing is moles. So when we throw all that into our calculator, we will get an answer of 2.57 moles. So we've got 2.57 moles multiplied by our molar mass, which is 44.02 grams per mole. Notice moles here cancel out to give us our mass, and our mass comes out to equals 113.13 grams. We want 3 significant digits, so it's equal to 113 grams of laughing gas is actually in the cylinder.